So I've been looking into ways in which we can measure intelligence of AI systems and humans and animals and develop this kind of way, what I call a predictive measure intelligence. So in my work, I'm linking intelligence to prediction, and I've got an algorithm that measures how effectively a system's predicting, making predictions about the future. So that's kind of my current work, and then hopefully, medium term, shall we say, that'll enable us to compare AIs, animals, and humans on a single scale, so we can do things like, judge whether humans or animals or AIs are more intelligent in particular environments. And also, I quite like the idea of using a universal measure of intelligence as a feedback signal to an AI, so we can train an AI to become more intelligent by itself.
Hello and welcome to a brand new episode of Engatica's interview series. I'm your host Dingu Sagar, and we are delighted to have you join us today. And today we have on our show David Gamez, an expert in artificial intelligence and machine consciousness, and a lecturer in computer science at Middlesex University. Welcome to the show, David.
Hello. Thank you for inviting me, Dingu. Very kind.
So before we get started, a little bit about Engatica. The Engatica interview series is a powerhouse of insights from industry experts and influencers from around the world. A platform that provides the latest news on AI, automation, and technologies that will help you grow your business. Come be part of our community. Let's learn, share, and grow together. So David, let's dive right into the questions. So my first question is regarding machine consciousness, because you are an expert in machine consciousness. So what does it mean to have what does it mean for a machine to have consciousness?
Okay. Right. Well, so I mean, in the work I've done, at least, it makes sense to sort of focus that question in different ways. Yeah. So there's I mean, in the work I've done, I sort of distinguish four kinds, which might be helpful to briefly recapitulate them, to sort of focus on which aspect you want to talk about maybe in more detail. Yeah. So first aspect is kind of machines that have an external behavior that corresponds to the external behavior humans have when they're conscious. Yeah. So there's a sort of set of diagnostic criteria for consciousness, for example, within psychology, neuroscience. And so patients can kind of, respond to questions in a coherent way, exhibit like a delayed response to stimuli, or do more complex stuff, maybe related to intelligence. Then they're judged to be conscious as opposed to unconscious. And then we're sort of very slowly, but not very fast, developing machines that can, to a greater or lesser extent, perform things that we can only do when we're conscious, right? So we've got AlphaGo, right? So someone who's in a dream state or, unconscious, or an epileptic automatism, which we can explain if you want me to, but if you're in an unconscious state, you're unable to play Go, right? Whereas a machine that's, when humans, when they're conscious, can play Go. And so a machine that can play Go is, to a very extremely limited extent, replicating external behaviors linked to consciousness, okay? So that's one sort of aspect of machine consciousness. Another couple of aspects I can probably lump in together are kind of models, either of, let's say, the neural correlates of consciousness, the kind of neural structures, neural activity that's going on when you're conscious. So we've built machines that have models of that used to control behavior and stuff like that. And we also have machines that are have models of our consciousness, you might say. Yeah. So these are machines that can kind of do things like imagination, sort of imaginative planning, this kind of stuff, and maybe the structure of the machine's minds to some extent corresponds to our conscious minds. Yeah. So those are sort of all sort of fairly straightforward, applications of sort of conscious science to artificial intelligence. And then you've got the sort of final category, which is the more kind of controversial one, which is machines that are actually conscious in the same way that we are, right? So when we're, as I'm, talking to you now, right, I'm experiencing colors, smells, sounds, all that kind of stuff. All of these are kind of components of conscious experience. These are kind of, in my case, distributed, loosely in space in different ways. And so possibly we can create machines that have something corresponding to that, right? That they probably won't be colors in the same way we have colors, because they're machines, they've got different senses and all the rest of it, but they have something a bit like our conscious experiences, and maybe they have unconscious periods as well. Yeah. So those are sort of, I probably completely forgotten your question, but those are different kinds of machine consciousness that we need to talk about. Yeah. And then you can, and then there's lots of different kind of questions surrounding each of the different types. Yeah.
Right. So before we go into the deeper, just like we humans take this term for granted, right? Consciousness. We say we have consciousness. So how do we define consciousness for humans, because if you see the latest AI deep learning models, it is able to generate images or like artistic work, which very realistic, and would attribute to human imagination, right? So how do we define consciousness in the first place, with respect to humans and maybe with respect to animals, so that we can compare it, and then maybe we can compare it, what how does it make sense to have a machine for it to have consciousness? Like, what are your thoughts on that?
Okay, so presumably talking about the last kind of consciousness, right? Rather than sort of
Yeah.
models of consciousness, right? Okay, so there's a sort of simple answer, and then there's probably a need to sort of dip a little bit into the history right now. So the
Right.
simple answer is most people say consciousness is the stream of experiences that appears when I wake up in the morning and disappears when I fall into deep sleep at night, right? Like I said, the colors, smells, sounds, etc. Yeah. But but to understand kind of what that means, I'm going to take a little excursion just to sort of set that in context a little bit, because people get very confused about this, and then it creates all kinds of problems, particularly in philosophy. Yeah. So okay, so the general claim, I would say, is that prior to the 17th century, we really didn't have anything like our modern concept of consciousness. Yeah. We sort of have what might be called something like naive realism. Yeah. So we look out in the world, we see some green stuff, and that green stuff is part of the physical world. Yeah. And most of the time we think that way when we're just interacting with the world. When I'm looking at these trees, which I can see out my window, I'm not saying that these trees are, in my consciousness, right? I'm just thinking the trees are green, and maybe I'll go and pick a green apple out of the green tree, right?
Right.
So prior to the 17th century, pretty much, I mean, obviously there's minor exceptions and complicated different traditions across the world and all the rest of it, but in Europe at least, people were pretty naive about it. They sort of saw the green stuff and said the green stuff was part of the physical world. But then in the 17th century, you had this sort of Renaissance, right? They rediscovered atomism, yeah. And so they had started to have much more sophisticated theories about the physical world. So they started to say, okay, well, the physical world's not green anymore. The physical world just consists of these atoms bouncing around in the void. And when these atoms happen to interact with the senses, then somehow, a miracle occurs, and I actually experience this green thing. Yeah.
Right.
So the 17th century, the sort of philosophers and scientists working then, they kind of stripped all these kind of colors, smells, and sounds out of the physical world, and then you just left the atoms bouncing around the void as like the physical reality. Yeah. And so
Right.
at that point, you sort of see this sort of bifurcation, you might say. You've got the physical world, which atoms in the void has that like, and atoms have like number, motion, whatever else is atoms have. And then somehow they had to fit, all these colors, smells, and sounds somewhere. Yeah. And so then you get this distinction between primary product qualities, which are kind of properties of the atoms, things like the number, movement, all this kind of thing. And then you have all the stuff in consciousness, and that gets put into this new sort of concept of consciousness, which emerges about that time. Yeah. So you get people like Locke and Galileo talking about consciousness containing all these properties, and so they can't like ignore it, because just the same way we can't ignore it. But they had to put it somewhere, and they put it into this consciousness thing. And there's some linguistic evidence for this. This person really like Wilkes does this sort of analysis of kind of linguistic uses of consciousness, and she makes the claim that I just said, that consciousness in our modern sense only really emerged, at the same time as the emergence of science. Yeah. So,
Right.
so that gives you the sort of the two angles on this, if you like. Yeah. One is the sort of how we actually talk about it and what we actually mean by all this stuff. So what we mean from this historical point of view is this kind of everything that's not physical that we experience from a moment to moment basis. Yeah. And then maybe we might as well sort of dip into this now. So from a sort of human point of view, that's kind of straightforward, right? Because we're immersed in this day to day. It's complicated, but roughly speaking, we can describe our conscious experiences. Yeah.
Right.
But when it comes to, let's say, animals, they can't. Yeah, they just do stuff. But because they have brains that are sort of loosely speaking similar to humans, we're quite inclined to attribute consciousness to animals just because they've got similar brains to ourselves. Yeah, the consciousness they will have will be different because they have different senses. What dolphins got, bats got sonar, right? God only knows what worms have. Dogs have reduced color vision, all this kind of stuff. Yeah, so this nature of the consciousness is likely to be different, but because the brains are roughly the same, And I'm pretty sure there's been some work on the correlates of consciousness in monkeys, at least, possibly not so much, possibly even just like flies, I think. But we can make rough inferences because they're similar, yeah. But when it comes to machines, they're completely different, right? I mean, we can build a machine from anything we like, right? We can make it out of bits of string and cardboard boxes or whatever. We can make a machine out of silicon. And so the question of measuring conscious machines is much more complicated. And very roughly, what we have to do is use a theory of consciousness, ideally a sort of mathematical theory of consciousness we develop on humans. And we can use that mathematical theory to make inferences about consciousness in machines. Yeah, I can go into more of that. But that's roughly the story with artificial systems, because there's a massive tendency, and I was just reading that article about the Google engineer who got sacked, right? But attributing sentience to the whatever that was, some version of, I think it was, the language model, right? But because there's a massive tendency of over projecting into things, right? They just behave in a apparently human way, but actually there's nothing human going on in there at all, and probably no consciousness going on either. Yeah.
Right.
So that's why you need a more sort of scientific approach to analyze the problem rather than just going on the surface level appearance of things. Yeah.
Right. So I think that leads to my next question. So from a scientific point of view, how do we measure consciousness? Is it something like binary, like a system has attained consciousness or it hasn't, or is it like a spectrum of values where you have high consciousness to low consciousness, just like IQ or EQ, right? We express them as scores. People who have high IQ and low IQ, medium IQ. So from a scientific perspective, have we come up with some models to measure consciousness, at least in humans, at least, so that we can, when it comes to like between humans and animals, if we can measure them, and then maybe to actually evaluate if a machine has consciousness, because there could be a case that the machine has attained consciousness and then we are not aware of it, or the other case that we think that the machine is conscious but it is not actually. So how do we quantify all these concepts? What are your
Okay,
thoughts on?
okay, let's focus on humans for the moment, yeah, because like I said, we can't reliably use the behavior of machines to measure their consciousness, and we can talk about that in a little bit if you want, yeah. But in humans, at least, we're willing to accept, we believe we're conscious, right? And we're also, one of our fundamental beliefs is that we can describe our consciousness, right? I mean, if we can't do that, the whole thing kind of falls apart completely, doesn't it? And then we have a very complicated thing to deal with if we can't describe our consciousness, yeah. So basically, at the bottom level, we believe we can describe our consciousness. And that's a good start, right? But unfortunately, it doesn't sort of get us the whole way, because actually, it's actually rather hard describing our consciousness, right? So in the naive way, I might say, okay, well, here I am, talking to you, looking at the screen and, listening to this stuff, yeah. But there's some pretty good evidence that our consciousness shifts about once every 300 or 400 milliseconds. Yeah, we have these kind of moments of consciousness, and then they shift, because our senses change or something changes, and then it's another moment of consciousness. So in a way, trying to describe something in natural language that's kind of shifting from moment to moment to moment is actually pretty much close to impossible. Yeah, and you kind of, there's a very sort of we may be aware of kind of saccades and eye movements. So eyes are kind of shifting around again on that sort of time scale of hundreds of milliseconds. We're resampling the physical world in different ways. Our consciousness is changing all the time. So what we end up with if we try and describe consciousness in kind of natural language is, a sort of a fiction, really. It's not like what we're actually experiencing in that particular moment. I mean, there have been attempts where people have like a beeper or something like that, and they're supposed to kind of write down what they're experiencing now. They're kind of trying to sample their consciousness in that way. But again, you get back into this trap that you're kind of looking back into your memory to try and remember, what you experienced, and you come up with some kind of fictional account of what your consciousness was then. Yeah. So even in humans, where we believe we can measure the consciousness, it's actually quite complicated to do so. So the kind of ways that probably work but are quite hard is more the sort of experimental approach, where you sort of use a sort of very carefully controlled stimulus, like a sort of an image just kind of flashed up on the screen or something, and then you kind of are asked to report on very small aspects of that stimulus within a short time frame. Yeah. So by using these sort of very controlled kind of experimental psychology experiments, we can then induce a state of consciousness, sample what you're experiencing about one aspect of it, and then on that's sort of realistic enough to be able to get a picture on a very short, on that time scale that consciousness actually works. Yeah. So that gives us some hope. But then the sort of problem that no one's really come close to solving yet is that, we sort of then need a way of actually describing that in a sort of fairly neutral way, should we say? Because if we describe things in natural language, that comes with a whole bunch of presuppositions. Yeah.
Right. I guess natural language description has its own information loss, right? Like if I taste something and I experience that taste, I can't write it in words. I mean, I can express it whether it's sour and sweet and etc. But the actual taste that I experience through the sense, I won't be able to express in natural language, right? So
Yeah.
I guess that information loss will be there. Yeah. So sorry, I wasn't.
No, you're completely right. You're completely right. It's exactly it. Yeah. And so if you say, that you're tasting, like you say, sour, sweet, and not only that, but there's the problem that people's tastes kind of differ from person to person quite a lot anyway, right? So your sort of experience of, jackfruit is the classic example, right? Might be different from my experience of jackfruit, right? And so we're in a way. So there's a huge So there's that, the fact that the information loss, which you correctly pointed out, and there's also the problem that when we want a description of consciousness that works not just for humans, but we want to make it work for animals and make it work for robots too, right? So somehow we need to find a way of describing it in more neutral terms that kind of can be applied to all the different systems. Yeah, and there's been a bit of work on that. So you may be aware of the work of Giulio Tononi, his information integration theory. So that's like a mathematical theory of consciousness. I mean, there's a lot of problems with it, but it does at least make the attempt to have like a mathematical description of a conscious state as this sort of high dimensional object. I mean, I don't buy it, but it's at least showing us the way, should we say, towards a more sort of neutral description of a state of consciousness. Yeah.
Right.
So just to complete the picture anyway, so we have these problems about recording consciousness in humans. We can't use natural language to describe it scientifically, right? We can use it informally between humans. I can say, that jackfruit tasted great. And you can say, yeah, it didn't taste so good. That's all good, but it doesn't work across as a scientific approach to describing consciousness. So maybe we can solve these problems and come up with a fairly neutral description language for describing consciousness. Yeah.
Right.
And then the other part of the puzzle is what's going on in my brain as I'm having those kind of conscious states. Yeah. And so there's been a lot of work in terms of what's called the neural correlates of consciousness, where they do experiments on monkeys, and people like Stanislav Dehaene have done an awful lot of work on this kind of stuff, where you kind of measure the neural activity as best you can. It's not easy. Neural activity is, complicated on a much faster timescale and much higher resolution than we can really measure at the moment. But best case scenario, we measure what's going on inside the brain at the same time as we're making these conscious reports. Yeah. Right. And then we can have a description of the physical world and a description of the conscious state. And then we can start to use, look for theories that kind of link the two descriptions together. Yeah. That's the sort of the kind of science of consciousness kind of moving forwards. Yeah. We solve the problem of description. We do the scientific work of, measuring what's going on in the physical world. And then we can maybe link these two descriptions together using some kind of mathematical theory. That's the hope here. Yeah.
Right.
On humans. Right. Yeah. And Tononi, that's why I'm sort of mentioning him. He's come up with a theory that will take the physical states and map them onto a prediction about conscious states. Again, there's lots of problems with the theory, but it does point towards, the way it's going. Yeah. And there's a community now on mathematical models of consciousness. About 200 or 300 researchers are all kind of looking into this different stuff. Yeah. And so that's the dream. And then I can answer the final bit of your question. Yeah. I'm going on a bit here. The dream is we have a mathematical relationship between descriptions of the physical world and descriptions of consciousness, yeah? And then once we've got that on humans, we can then use that to make predictions about consciousness in artificial systems as well, yeah? Because remember, it's mapping between these two sets of descriptions. So it might say, if my brain is in this state, I'll be having this conscious state, yeah? Mm-hmm. And then we can then take it to an animal, for example, and say, well, if this animal is in this particular physical state, we can maybe make a prediction about its consciousness using our mathematical theory, yeah? Right. And then we could do the same thing, as you can see where I'm going here, right, to a machine, although machines are very, very different. And there's lots of complicated problems about taking a physical description at the level of biological neurons and trying to apply them to machines, but let's not go into that. In theory, right, we could do the same approach with the machine. We could measure its physical states and then use the mathematical theory to make a prediction about its conscious states. Yeah.
Yeah, just a doubt. So when you say measure the physical state, what do you mean? Do you mean measure the brain activity or something like
Well,
that?
that's
Or
the $1 million question, yeah. So most people focus on neural correlates of consciousness, yeah. And then, but that's not very generalizable. Again, you've got the same generalizable problem. It's fine for humans, right? We want to know if
right,
coma patients are conscious or not, and that's useful research, nothing wrong with it, yeah. But if we want to generalize it to machines, we have the problem that, okay, what is a neuron exactly, yeah?
right,
And then you have the whole sort of synthetic biology, right? Is a crab neuron the same as a human neuron? If we knock up a neuron from scratch with put some ion channels in it, is it going to be the same or not the same? So the more generalizable theories, even though they're not very well backed up by evidence at the moment, are things like electromagnetic theories of consciousness, right? Which exist, but no one's really done any proper research that I'm aware of on trying to find electromagnetic correlates of consciousness. But there might be, right? And in which
right,
case, we could then look at the electromagnetic patterns in the system and then see if they correlate with consciousness or not. Yeah, because biological neurons, it might be the biology that's crucial, right? And people like Hameroff talk about quantum states, quantum processing in microtubules and all this biology stuff. Or maybe it's not, right? Maybe it's just the electromagnetic pattern they produce that correlate with consciousness, or the quantum stuff,
right.
And so we haven't done the work. We're at the very early stage of all this stuff, but we need, if we can pin down exactly what it is about a brain that is linked to consciousness, then we can look for that elsewhere in the physical world and see if it exists there
Right.
as well.
Right.
And it
So,
might turn out that biological neurons are the crucial thing. Everything has to be there, and therefore we could just say, well, no machines are conscious. Done and dusted, right? Most likely not.
right,
Most likely it's more subtle than that, right? But we're a long way from knowing, what the actual physical correlates are at this stage. Yeah.
right, right. It's interesting. It's like our brain has all the answers, but we are just scratch the surface of it, right?
Yeah,
So,
totally. Yeah, yeah. Well, it's
yeah,
very early stage of this stuff, right?
yeah, right. So, coming to my next question. So back propagation is the learning algorithm, which is like popularly used in all the deep learning uh, models and during the training process, right? So, do you think back propagation is a way of modeling, is in the right direction of modeling human brain, or are we oversimplifying it a lot uh, by
Well,
using
okay.
this?
So it's a classifier. It's often used for, right? I mean, in a
Right.
simple classic case, right? And most of the even things like reinforcement seem to me to be mostly the same sort of feed forward and then training with the feedback,
Mhm.
right?
Right.
So obviously the brain doesn't really work like that. The brain's much more complicated. I mean, obviously, okay. So first off, deep nets are inspired by brain architectures, right? In a loose way. Yeah,
Right.
we've got all that sort of solid science of early visual system, right? Where we're detecting edges, and if you train a network up appropriately, you'll find at different levels of the deep network there'll be like the corners, and then there'll be probably gratings and stuff like that, and then you work your way up to maybe hands at some level, maybe, and then you work up the way up to bodies and people or whatever, yeah, or all that kind of
Right.
creepy, deep dream stuff, yeah. So
Mm.
in terms of the sort of, and I'm guessing that a lot of this kind of work on deep nets. I mean, there's sort of various tricks and hacks that made them viable in the last 20 years, say. But setting all that aside, they're sort of loosely inspired by this work on the human visual system, right? And then obviously being generalized because you can do it to any kind of patterns and it'll generalize them in the same kind of way, yeah. But the human, but firstly, okay, so the big difference, obviously, between the deep nets used, in machine learning at the moment and human brains is that human brains are spiking dynamic systems, right? So they're all based on, neurons that fire, patterns of spikes, which you don't fully understand at the moment. And these spikes interact in kind of complex dynamic ways with the rest of the brain. And the brain is way more complicated than any deep net is. So even if we're talking at the sort of early visual stages, there's sort of some very substantial differences. And when I saw your question by email this morning, I had a quick look. And so people are exploring ways of building deep nets out of spiking nets, partly to see if they can make them more realistic, but also because spiking nets they're much more efficient, right? Because when the neuron's not actually spiking, it's not producing it's not consuming electricity. You don't have to model the entire neural network. You only have to model the neurons that are actually active. And also, there's a lot of work on what's called neuromorphic hardware, where they're building specific sort of chips that can model spiky neurons much more efficiently than, because they can use the sort of the electronics, the flow of electrons, using capacitors and stuff to model the neurons at a very kind of low level. So in terms of just the models of the neurons, and there are ways in which they're looking at maybe mapping that onto brain architectures a bit. And actually, I've been reading stuff all on the predictive brain in the last week. So the predictive brain is so the deep nets are kind of a bottom-up model, right? You feed in stuff, you have these layers, and at the top you have the the thing that occurs, and it's kind of course, whereas the predictive brain sort of flips that over, right? The idea of the predictive brain is that the brain, each layer in the brain, is not just trying to classify, but it's trying to make a prediction about the layer below it, and it gets like an error signal being fed up this kind of hierarchy instead. So deep nets don't really work that way, although the backpropagation algorithm could be seen as a sort of predictive thing at the top, which is then being matched by the different layers going down. So there's some kind of correspondences with this sort of idea of the predictive brain. But maybe also it's still, people think of it a lot in terms of bottom-up processing, and maybe real brain architectures, which are actually, there's many more connections going down from top to bottom in a real brain architecture. Whereas I suspect in deep nets, it's more like total bottom-up feed forward kind of approach, right? So there's differences, but there's useful overlaps. Maybe does that half answer your question?
Yeah, right. I guess there's like a lot of stuff to explore and a lot of new things to be discovered, right? It's a very interesting field. We can keep talking on this forever, but yeah, I guess the time is also coming to an end. So we would like to end the interview. Before that, do you have any other sound bites you would like to share with our audience? Uh, like, do you want to talk about your book, Humans and Machine Consciousness?
Well, okay. Well, I will say that the stuff I've been trying to explain loosely and probably too fast is kind of explained, in that book in quite a lot of detail. Oh yeah. Well, I'll just say something that I'm working on now, just out of interest, really. So we're talking a lot about the kind of consciousness, artificial consciousness stuff, but and so I've done a lot of work on that, written the book, and I still write the odd stuff on this. But my main interest now is on a universal measure of intelligence. That's what I'm working on at the moment. Yeah. So right now we have good measure. Tell me to stop if I rabbit. A couple of minutes. Yeah. Okay. So right now there's been a lot of work on kind of IQ measurements in humans, and some work on measuring animal intelligence, and a tiny amount of intelligence tiny amount of work that's trying to measure intelligence in artificial systems. Yeah. But we don't really have a good way of measuring intelligence of AIs, animals, and humans, and comparing them in different, so we can see, whether AIs are more intelligent than humans, whether they're going to overtake humans in some kind of apocalyptic, singularity scenario and all that. Yeah. So I've been looking into ways in which we can measure intelligence of AI systems and humans and animals, and develop this kind of way, what I call a predictive measure intelligence. So in my work, I'm linking intelligence to prediction. And I've got an algorithm that measures how effectively a system's predicting, making predictions about the future. So that's kind of my current work, and then hopefully, medium term, shall we say, that'll enable us to compare AIs, animals, and humans on a single scale. So we can do things like, judge whether humans or animals or AIs are more intelligent in particular environments. And also, I quite like the idea of using a universal measure of intelligence as a feedback signal to an AI. So we can train an AI to become more intelligent by itself. So I think it's quite an exciting area in terms of moving forward with artificial intelligence. Yeah. So it's a bit off ball with your questions, but I thought I'd throw it in, because that's what I'm working on right now.
Right. I mean, really interesting topics. We had a really good conversation, and thank you for sharing your valuable insights with us. So for more content, viewers, you can subscribe to Engatica and tap the bell icon to get access to exclusive content from thought leaders around the globe. Thank you for tuning in. We'll see you with a new expert soon. Thank you.
Thank you. Many thanks, Dingu. Much appreciated.
Thank you. Yeah.